So a couple other properties that we can look at involving first-order reactions is, well, one question that we might want to know is, what is K, right? How do we, if we measure something like this, how do we determine the rate constant? So if we have a plot of concentration versus time, we can actually just directly fit this to an exponential function. There's lots of software that allows us to do this. It's similar to the idea of a least squares fit of a line. And that would allow you to determine K. That would be part of the fitting routine. So that's one way to directly determine it. Another way, if you want to use lines, is you can sort of transform your equation into a linear form. So we can go back to the natural log form of the equation and say, okay, natural log of A is equal to the natural log of A naught minus kt. This is just reorganizing the equation we had in the previous video. And if you plot natural log of A versus t, this will give you a straight line. So ln A versus t, you will now get a straight line with a slope of negative k. Okay, and so that's another way to determine K is either you directly fit the exponential or you can transform it into a natural log versus time, get a line, and fit that line instead. Whichever works easier for you. Okay, so one of the other useful characteristics to know about first-order reactions is the idea of a half-life. So you've probably heard about half-lives before in the context of nuclear chemistry, right? So radioactive decay happens, so the kinetics of radioactive decay is first order. So it just depends on the concentration, not raised to any powers, just raised to the power of 1, of however much of your radioactive substance you have. And so this half-life idea is often used to describe radioactive decay, but it also applies to chemical reactions that are first order as well. So a half-life is when your concentration of A, or whatever you're looking at, is equal to half of the initial concentration, A naught over 2. And so we can go ahead and substitute that into our equation. We can say, okay, well, the natural log of A over A naught is equal to minus kt. Once we can just plug in at this specific value of A, what does our equation look like? So we can write natural log of A naught over 2 divided by A naught is equal to minus kt. We'll call this t 1/2, meaning it's the time at which we'll have half of our initial amount of substance, our initial reactant. These A naughts are going to cancel, so we'll get the natural log of 1/2 is equal to minus k times t 1/2, and then we can solve for t 1/2. Okay, so the natural log, so we'll get t 1/2 is equal to the natural log of 1/2 divided by negative k. And we can rewrite this. The natural log, natural log of 1/2 is equal to negative of the log of 2. So we can write this now as positive log of 2 over k, or we can plug in the specific value, which is 0.693. And of course, there's more to that, like if you need more accuracy. So this, oh man, just trying to draw here. Okay, so 0.693 over k. So what's interesting about, for first order reactions, the half-life, and one reason why this is often, instead of being told the k value for a radioactive element, you're instead told the half-life because the half-life does not depend on A naught. So half-life is independent of how much substance you have. It's just a fixed value that depends on the rate constant for your reaction. And so no dependence on concentration. I promise I'm writing all these words. They're just not not all coming through. Okay, concentration. Okay, so that's specific to first order reactions, that you have no concentration dependence in terms of the half-life. And so the half-life is directly determined by the rate constant, so you can sort of characterize the reaction either way. You can talk about the half-life, or you can talk about what's the rate constant. They're directly related to each other according to this equation. In the next video, we will look at second order reactions and their properties.